So if we now go back to equation 30, which we see here, so again talk about your pin-ended strut, and then if we said that the pin-ended strut wasn't perfectly straight, and it started off life with a deflection at the center, not a deflection, an initial imperfection A. So when you've got your load at 0 kilonewtons, so your unloaded strut, it starts its life off with with an initial imperfection of magnitude A. If we now go back and look at equation 28, 28 is about the additional deflection. So if we had a larger deflection, and then I put a dotted line representing the initial deflection, so just draw that line there. So that dimension would be your A. Okay, so the dotted line, so that is the perfect condition. That's the real initial imperfection of magnitude A. And I'll just remove that now that we've defined what it is that we're talking about. And we're sticking a load on. So we're sticking an additional load on. So that's P kilonewtons, and that would be P kilonewtons. So we're moving from the 0 kilonewton state. I'll get rid of this line there as well, just to show the exaggerated imperfection. As we talked about yesterday, these imperfections are not detectable to the naked eye. So you may need to use a laser scanner these days or something else in order to measure it. So whilst they are very small, they're obviously essential to the calculation, because if they weren't present, then all that would happen is that your strut would shorten. So if there weren't any initial imperfections, then if it was perfectly straight with that load on, so obviously not perfectly straight, you stuck the load on, all that's going to happen is that your strut is going to shorten in length, yeah, and it would still be straight. Okay, so the initial imperfections are very important for the mathematics as well as for what happens in reality. So now at mid-height, we're talking about that deflection there, delta. So that would be the mid-height deflection, not the total deflection. And here we can see that the mid-height deflection delta when x is L over 2. So let's just start that there. So that's your x-axis. And when x is L over 2, which is the halfway height, then that initial, that additional deflection is going to be equal to the magnitude of the initial imperfection, because that would be your V0 at L over 2, PCR over P minus 1. So we'll say that that is equal to A divided by PCR over P minus 1. So when your P is very small or 0, then that becomes infinity. Infinity minus 1 is infinity. A divided by infinity is 0. So when the load is very small or a very small load, there's no additional deflection at the center. So that's where that equation comes from. So sometimes I am asked, when you see the PCR over P and you see the P over PCR, whether that's an error or whether that's a typo. It's not a typo, and you can work through the derivations if you want to. Anyway, that's equation 30. So now we come on to what's known as the Southwell plot. So that equation, delta equals A PCR minus 1 over P. If you now divide top and bottom of that equation, if you divide both sides of the equation by P, you can then re-express it in this form here. So why is the Southwell plot important? The Southwell plot's important because sometimes you don't know what PCR is. You may not know what PCR is. You may not be able to do a test or a test to destruction to work out what PCR is. So the Southwell plot allows you to stick small amount of additional load P, so you could just say 1 kilonewton or 2 kilonewtons. You just measure the additional deflection, which would be delta, for that load level, and that would allow you to be able to predict what PCR is. So let's just read it through. There's a linear relationship between delta over P and delta, which when plotted is known as a Southwell plot. So you can see the Southwell plot here. It permits experimentally the buckling loads PCR from a series of load and corresponding deflection measurements at loads less than the buckling load. So you don't need to destroy the section to work out what the buckling load is. Thus the buckling load can be determined without actually buckling the column and damaging it. So again, I know that's not what they're doing with the bridge in Auckland, but that's what they might be able to do if they wanted, I suppose. They could stick on an additional load, measure the additional deflections, and from there work out what the implied PCR is. Remember, PCR is elastic. So example 3, a strut is subjected to an increasing axial load force P in one of our testing machines, and the resulting delta increments in mid-height lateral deflection is as follows. So this has all been tabulated with the different values of P which you've stuck onto it, as well as the additional deflection delta. What is the predicted buckling load from all of this? So you would do the Southwell plot. You've got delta over P against delta, so we're plotting Y on that axis, and then and then on this axis here we're plotting delta, so that becomes Y equals mx plus c, so that obviously becomes the interception, which you're not so worried about, and then that would the 1 over delta c would become the gradient. So to do this, you just get these numbers and then you divide the delta by the P, and then you can tabulate that value there. That would be your delta over P, and then you would plot that on this axis going up here. So that becomes that. So I know that says N, but N is also an axial load, which is shown here, but just replace N with P. And then you plot that against delta, which we see there. And then with these data points, you can see they don't exactly line up, but you can draw a line of best fit through them. Now, once you've got that, you can work out the gradient. You can work out the gradient of that. So that would become from your Y equals mx plus c. That would become the gradient m. So you draw your line, work out the gradient between any 2 points of your line. So work out the gradient m, and then that becomes the inverse of this, and then PCR becomes the inverse of the slope. So you can calculate there just by doing the reverse, and then from there you work out that from your experimental test or your non-destructive test, that PCR is 13.85. So that's a way that you can use, you can test something experimentally, and without destroying it, you can work out what the load is. So I showed one of our papers yesterday where we have tested some columns in our laboratories here. So we'll tested that column. We'll come onto the position of the load later on, because that's very important. But if you flick through it here, we can see you're applying the load. And over here, we didn't use the Southwell plot, but these would be our lines of load against deflection, axial shortening, or the axial load there. And we've also got points taking the extension on one side. So from those, you would be able to use the Southwell plot principle, and to be able to estimate the elastic critical buckling load without necessarily taking your structure to failure. So that's what's known as a Southwell plot. Okay, so let's now move on. So we'll now move on to eccentric compressive loads. So going back here, we're testing channel sections there, and down here we've got some pictures which would be showing the test setup. You can see the load is going through that point there, so your load through the 2 pin ends would be coming through there. So you could sort of imagine that you've got your C-section going through there. So if your C-section was like that, say, and if, say, you were able to work out using civil211, and you were able to work out the center of gravity of that section, and suppose it came out there, the question is, what happens if your applied load, so let's say your P is applied there, going straight down, what if your applied load is not exactly at the centroid of the section? And this, of course, is what happens in reality. You can't really expect the loads to be applied directly through the centroid in any structure that you may find. So that's what we've got there, eccentric compressive loads, where the load is applied off the centroid. So far we've assumed the compressive load is applied at the centroid of a cross-section. Thus again, it's unlikely to be in the real structure, because they cannot be built in such a way that the loads are not applied through the centroid, or even if it loads act normally through the centroid, in reality there can be accidental misalignments leading to load eccentricity. So we now explore how we can use what we have or what we've developed in order to take that into account. So we're basically just going to be lumping everything together. We know that there are geometrical nonlinearities which may need a laser scanner to help you overcome, to find out the magnitude of the geometrical imperfections. We know that there are material imperfections, and that you can't expect the section to be, the material properties of the section to be completely the same. There's always going to be some natural variation in them. There are residual stresses, particularly in steel sections when they're loaded. So these residual stresses arise during the cooling process of the steel. So when you get your molten ignite and you turn that into your steel section, you're going to be trapping in some stresses, and these stresses can be almost as high as the yield stress. And of course the residual stresses are not the same in both directions. So we talked about before, there's no such thing as an absolutely perfect column, and a real column is going to have geometrical nonlinearities, it's going to have imperfections, residual stresses, the material properties are not going to be the same in all these directions. And as engineers, we just need a pragmatic way in order to deal with all of these problems. Putting that aside, you've also got the issue as to how to actually apply the load, or where the load is applied. So here we can see that we're assuming that the load is not applied through the centroid of the section. So you can see there's an eccentricity to the point of load application. And we just go back to the fundamental theories as to how to handle this. So the moment curvature relationship is, as we've had before, with minus mx, and that's equal to p times the whole displacement across plus the e, simplified of course to v double dash x plus alpha squared v of x is equal to minus alpha squared e. This is an inhomogeneous equation, and then we can look it up. It would have the following solution for pin columns. So don't worry, this is not a maths course, so we're not going to be testing you on the derivations. But if you do want to know, firstly, derivations are not examinable. You've covered it all before in mathematics courses in earlier parts of your degree program, probably in the first year. But just if you wanted a recap as to how to solve these equations, we've put them all there. Okay. So hopefully you can accept that the equation is of this form. V of x is equal to eccentricity cos alpha x 1 minus cosine alpha l over sine alpha l, sine alpha x minus 1. Just to remind you, we are of course dealing with radians. So sometimes in the past, when some students have tried to put some numbers through these calculations and find that they're wrong, the reason why they haven't made an error, they were just using degrees in their calculators. You should always be using radians. So just bear that in mind. So the mid-height deflection, which would be this delta here, so the mid-height deflection is then given by this equation here, just basically by substituting in L over 2. So you can see there's a cosine 2 to pi over 2 P over PCR. So there are questions in the course book that need you to calculate this. So please just remember, have your calculator in radians when you do the cosine bit of that function. So let's graph it. So figure 10 shows the graph. If your column, if the load is applied directly through the centroid, i.e. almost with an eccentricity of 0, so we know that that's almost impossible. We would never be able to do such a test to that accuracy in the lab. The load path that would happen for your deflection at the bottom, the graph would just would go up that vertical axis, and then suddenly at PCR the deflections would shoot off to infinity. Of course there will be axial shortening, but it would go up almost along the axis here, and then it would shoot off. Now if your eccentricity is equal to E1, where E1 is less than E2, we're just showing if we can introduce some values of E there, the graph, instead of going up and then sudden failure, there's a more gradual failure, or there's a failure that can be expected, as you can see the load going up and then going down from there. So when E is 0, it's very, very sharp. It's suddenly at the point where the things like when it's reached PCR, pi squared EI over L squared, everything suddenly shoots up to infinity. If the eccentricity is E1, which is not a very big value, then the curve is going to be more rounded, and of course all of these would approach that value in the end, since a column can't take more load than PCR, and if the eccentricity was larger, it would be like that, and so on. So if you had a smaller eccentricity, it would look like that, and then if you had a larger eccentricity, it would look like that. So this is where, as engineers, we try to be pragmatic. We want to provide design guides. So one design guide would be the AU-NZ 4600, which is a code which engineers would be designing to, and you would be looking things up. And within that, it will give some recommendations as to what the engineering community say you can be using for the eccentricities. So that's how engineers are pragmatic in terms of codified solutions. Anyway, let's go on. So the above formulas for eccentrically loaded columns were derived for the particular boundary conditions of a pin-pin column. So same as before. So this is just pin-pin, as is emphasized there. Care must be taken when analyzing columns with other boundary conditions, and generally appropriate relationships need to be derived from scratch. If one does so, it turns out that for a cantilever column, one can use equation 35, where delta would denote the deflection at the tip. So a cantilever column might be something like that, with the column and then with the load coming down, not going through the centroid but with an eccentricity. So you can derive these equations from scratch, and if you went through the exploratory problem sheets, you would come across some examples. But as I've said, you know, derivations are not examinable, so don't worry too much. And anyway, it's an exploratory level problem. So we now come on to BC EX4. So a pin steel column of length 7.8 meters is constructed from a wide flange shape. So with cross-sectional area A, second moments of inertia in both directions are given, and we talked about this elastic moduli. So before we go on, just remember all of this, the terminology of Z, the terminology of second moments of area, which is the same as moment of inertia. All of that has been covered with Lucas and Quincy back in Civil 210. So you may need to have a recap on those if you're not sure about anything. If you flick back through the course book back to the start of the course, there were some questions within here. So for example, that question would have required you to work out the cross-sectional area of the cross-section. Let's go through here. So the basic skills test of 2014, it requires you to use method of sections, method of joints. I just mentioned that now at this stage because when we come into virtual work, we're going to be looking at trusses. So again, back from Civil 210, and also what you did in your first year in terms of being able to calculate forces in trusses. And it also has a recap as to calculating second moment of area or moment of inertia about the x-axis, about the y-axis, about the z's and the z's, and which axis is stronger. So in this case here, the x-axis becomes the major axis, and the y becomes the minor axis. So if you're not okay with that at the moment, I would suggest you go back and do some revision, or at least go through this example, and that's probably all you need to do in order to cope with this. So the column is subjected to centrally applied loads and an eccentrically applied load P. The load P2 acts on the bracket at the distance S, which would be your eccentricity, from the centroid of the wide flange cross-section. And this figure here shows sketches illustrating the problem. Bending occurs about the 1-1 axis of the cross-section, and the eccentric load acts on axis 2-2. And here it says take E as 200 GPa. So if you now go onto the Dropbox, so if we go into the Dropbox, if you go to part 3, buckling of compression members, which would be there, you can see the in-class questions. So there are solutions to all the in-class questions there, and we're on the in-class question 4 at the moment. So if you have any problems finding the Dropbox or finding this precise folder, let me know. Now within here, you'll see 2 solutions. This one here is one solution. So maybe some of you just want to look at that and then you're absolutely fine, you don't need more details. There's a longer solution which I've got here, so I'll talk about the longer solution a bit later on. So my longer solution is here, and if you wanted to listen to a lecture recording that talks you through the solution as I write it line by line, you're more than welcome to go to the YouTube links. So I've given 2 YouTube links there. So that would cover where you can find this particular problem. So because of that, I won't completely go through it here, but I'll just talk about the solution. So here you've got your pin steel column, a wide flange shape, so you can see that if we drew that down there, we've effectively got an I section, which I've sketched there. Okay, so we've got that I section here, which there, and onto the I section, what they've done is they've welded a bracket on top of onto the I section. So you would maybe we would say that the bracket could look something like that, for example. So you've welded a bracket onto the end of the I section, and then you're sticking your load on right through there. So looking at it in that direction there, we can see an eccentricity. So there's an eccentricity to the centroid of the original cross section. So that would to the centroid of the original cross section, which I'll show there. So I'll get rid of that for the time being. Okay. So now if you had a column like that, let's say, I know it's not what the question says, but if you have that, and then eccentrically you've applied a load, obviously it's going to be bending in that axis there. So as the column goes round, okay. So you can see it's going to be bending about that axis. Okay, so we've got at least that portion of it is going to be bending about that axis, and it's not going to be bending about that axis. So in this question, they've called this axis 1, 1, and this axis 2, 2. So if we wanted to use the word major and minor, or strong and weak, 1, 1 is the 1, 1. Just by looking at the shape, you can identify that as being the strong axis, and 2, 2 is going to be the weak axis. So 1, 1 is the strong axis, at least as far as that configuration goes. So there's something called a red herring, which is when information is given that is not actually needed. So we can see as you read the problem, we can see that it does give the section moduli 1 and 2, but because we know that the section is going to be bending about the 1, 1 axis, maybe the two bits, the Z2 and the I2, which is given there, maybe or maybe not, it's not actually needed in terms of the calculation, and maybe it's what's known as the red herring. Okay? So if you've not come across the term red herring before, just Google it, and then it's not an engineering term. Just Google it, and you'll see what I mean. So the column is subjected to a centrally applied load. So we've got one load, which would be applied at that point there, and then we've got another load which would be applied at that point there. So the centrally applied load right at the centroid of that section, that's going to be 1420 kilonewtons, and then the one that's here is going to be your 180 kilonewtons. That's going to be applied right at the end. So I'll put the bracket back, okay, into the sketch. But that's basically what's happening. You've got one load coming down here through the centroid, and then you've got another load coming down there. So bending occurs about the 1, 1 axis of the cross section, which we've said already, and the eccentric load lies on the axis of the 2, 2, So the eccentric load is acting there, which is on that axis there, but we know that the whole thing is going to be bending about 1, 1. Take E equals 200 GPa, and then again find the maximum compressive stress in the column. So before we approach the problem, one of the first things that we can do, could do is maybe we could add the two loads together. So we could say 1420 plus 180, add the two loads together, and then divide that maybe by the cross-sectional area or something, and then that would be the total axial stress. So we could that's almost like saying let's move the P2 load so it's also through the centroid, and then ignoring any buckling or ignoring any additional deflections. For example, we would be able to work out the axial component of the stress. So perhaps just as a starter, 1420 plus 180, that will give you a total force, and divide that by the cross-sectional area, 1.55, and then that will give you a stress. That would give you the stress. So that would be the axial component of the stress, but that of course ignores this bending component of the stress, influenced of course by the fact that a column wishes to buckle, and also that there is an eccentric load being applied on at the bracket. So this is what we have here. So we've got our column, 7.8 meters, pin at the ends. These are the properties that we've been extracted, including the Young's modulus of E. Here is what I've just said. You've got the two loads coming down on both sides of the bracket, with the 1420 being applied at the centroid of the I section, and the 180 being applied right at the end. And then here is the explanation for the weak and the strong axis. So the stress is going to be your force over area. So that's going to be the axial component of the stress, which you will get by P1 plus P2 divided by the area, and that would turn out to be 103. And onto that you need to add on your bending component, your bending component made up of a moment, and of the bending moment, and divided by the Z1. So that again goes back to what I said was the red herring. So the red herring is perhaps the Z2s, that information there, and that information there, the minor axis, maybe that one, maybe this bit of information is actually not needed in order to solve the problem. So let's go through the calculation. So again, drawing out the bracket, and then down here working out the bending moment. So the bending moment is obviously going to be, you want the bending moment from here along the centroid. So the bending moment caused by the 180 would need to be multiplied by the 350 millimeters to work out the bending, which is going to turn out to be 63 kilonewton meters. So now we've got the eccentricity, which we see there. And we're going to be able to need to work it out. So the eccentricity E is that moment, and that's equal to 63 kilonewton meters, and then you divide that by the 1600, and you get 39.4 millimeters. Right here, I've drawn what the deflection might be. So we've got the load being applied at the end here, and first things first, of course, is to work out what the PCR is. So you work out what the PCR is. You got pi squared EI. Remember, it's I1 because it's bending about the major axis. So pi squared EI over your L squared, where your L squared is 7.8. And then from there, you can calculate what PCR is. So note that okay, I was going to talk about whether that's below the yield stress or whatever, but we'll leave that until the next lecture when we bring in plastic properties into the conversation. So up to now, everything has been elastic, and we've not talked about anything going beyond the yield stress. So you can work out your P over PCR. So we know the P that we've applied, which is 1600, the total P, and then we know what PCR is because we've just calculated it. So we're saying that the ratio of P over PCR is 13% or 0.13. So this means that the load P is nowhere near to the buckling load. It's nowhere near to the 11907. It's only 13% away from that, but nevertheless, any column under any axial force, the effect of buckling but needs to be taken into account in the calculation. So right here we see that equation that we talked about previously. So let's go back down to the course book, and then we can see the cos pi by 2 multiplied by P over PCR. So remember, of course, that when you multiply this out, you're going to and take the cosine, it's all going to be in radians. So right here you can see that we've got 1 over cosine of pi by 2 multiplied by 0.13, or the square root of that, which we calculated there, and that's going to be -1. And then from all that, once we've got our deflection, which is there, plus the eccentricity, because that's the distance away from it, you can go back to your moments. So we've got P over A 103, M over Z. So we worked out what the M over Z is. So M is the bending moment, which is 1600 kilonewtons. That's the complete applied load, and you've added that to your deflection plus the E, where that one comes down. So that one is your moment arm of the force coming down. So you put that back into here, and then you get your 103, and then you get your 37, and so the total stress that has been applied is 140.8 newtons per millimeter squared. So I've gone through that. I've just really tried to explain the calculation, but of course, if you wanted to go through the YouTube video, I would talk in more detail about how these numbers have come around. So there were some questions about this one in previous years. If you get the file from the Dropbox, I've extracted some of the questions. This question is basically about the axis, because the red herring that I talked about, whether you use I1 or I2. I've answered the question by saying in the question it states that bending is about the 1-1 axis, so you're using the I1 and the I2. Then I've also made a note, if nothing is mentioned, you should use the lowest value to calculate the critical stress. You know that your bending is critical with respect to a certain axis. You of course try to optimize your design for the relevant section properties. So for exam questions, take I and Z with respect to the axis which is given in the question, and take minimum if nothing is given for safe design. So that's the response to that question. And then there was another one saying it's almost the same thing, why the major axis was used to calculate PCR, and then it says bending about the 1-1 axis, so you have to use 1. So again, that's almost the same question. So that's the normal concerns over that question, apart from the need to calculate things in terms of radians. So we'll move on. So up to this point, everything has been elastic. Okay, so everything until this point has been completely elastic. Going back to the experiments that we did at the university here, I talked about the coupon test yesterday. So you should all know about coupon tests anyway from Civil 211, or just materials, but here you can almost make out the coupon that's here, and then in this test we're putting it under tension, of course. So we're pulling the coupon apart in the so that it's under tension, and then it would neck, and then eventually it would fracture. So when we do these experiments, we plot the stress strain curve, and we can see that for steel, we can see the yield stress is maybe about, or the ultimate stress is maybe about 300, certainly less than 400 newtons per millimeter squared. So it's quite a nice idea to have these things in your head so that you've got a reference point. You know that the Young's modulus for steel is about 200 times 10 to the 3 newtons per millimeter squared, and you would know that your yield stress, of course, would be under the ultimate stress, and you would know that typical values would be about maybe 300, ranging all the way up to 500. But at least you know the ballpark figures for these things here. So up to now, or up to this stage in our calculations, when we work out pi squared EI over L squared, we've assumed that everything is in the elastic range. So if you remember from the last question, we worked out that factor 0.13. Well, that means that your load level, or the load, is only 13% of what your buckling stress is. So we've got our PCR is equal to pi squared EI over L squared, so for your buckling load. So typically, if you divide it by PCR by the area, so if we divided the area and then we said that was equal to sigma CR, or the stress of the section at which buckling occurs, or at which the member becomes unstable, we've assumed that it's going to be up here. Okay, so it's typically much higher than the yield stress of the material. So now we come in terms of our discussions, and we want to talk in terms of maybe a unified approach. A unified approach means that we wish to take both the material capabilities or the material strength as well as this buckling into account when we come up with some design guidance for columns. So we've already shown that pi squared, that PCR is equal to pi squared EI over L squared, and we've said that's all elastic, and then we've talked about the slenderness before, about combining the L and the I, or the L and the radius of gyration for the slenderness, and then if you divide the PCR by A, so you divide all of that by A, we're going to be getting the elastic critical stress. So let's now plot this for the elastic critical stress. So here we've got a stress there, and we plot that against our parameter lambda, where lambda represents what the length is. So if we flick back through the course book, back to where the lambdas were talked about, where we came across lambda, lambda being our slenderness, so this was just before the mid-semester break, and then your lambda is equal to the effective length over R, so L effective, which for pin is the same as L, divide by R, where R is equal to the square root of I divided by A. Okay, so I normally just think in terms of lambda being the same as L, at least how I think about it. So you've got a graph here of the critical stress on the y-axis, and then you've got an axis here which represents the length of your structure. So when you're in this region here, the length is going to be very small. So you've got a very small length under that, and then when you're back in this lambda here, when the slenderness is large, your length of your specimen is going to be very long, at least compared to what the length was there when the slenderness is low. So when someone says, or an engineer says, it's got high slenderness, they mean you're in this region of the graph, and when they say that it's very stocky or it's got a very low slenderness, you know that you're in this region of the graph here. So this graph, as you can see, can be plotted. So why do we want to plot it? We want to plot it so that we can also start thinking in terms of the yield stress of the material, or the fracture of the yield stress and the ultimate stress of the material. So I'll get rid of that so that it's a bit clearer to look at as we chat. So I've just shown the graph of stress against strain for the coupon test. So this is how steel behaves. There's a plateau, and then after the plateau it goes up, and then it fails there. So that one there, if that one is called the yield stress, this one is called the ultimate stress, or something to that effect. So Y is yield and U could be the ultimate. And as we can see, when it comes to buckling, we're only concerned with the yield stress. And we're only concerned with the yield stress because once it reaches the yield stress, even though it does rise up later on, just one of the peculiarities of steel, along here there's zero stiffness. So here you're moving up here, it's the same stiffness, same gradient of E, and then when you reach the yield stress, there's a horizontal plateau. So suddenly your material has no strength. So it's gone from there to there with no strength at all. And that's when your structure can buckle, because there's no strength here you've got E, and then here the gradient there is E, so it has some stiffness, and then here your gradient is 0. So that's why no matter how high the ultimate strength can become later on, once you've reached this plateau there, which is defined by the yield stress, your column basically has it, and your deflections and everything with 0 stiffness, everything would be shooting off to infinity. Okay. So that's why we're only concerned with the yield stress, and why we're not talking about the rest of the graph there, which I like what I showed in the experimental tests or in the experimental measurements. So I use the term unified. So here we're going to be unifying the instability of the material, and we're going to be unifying, the instability of the member because it wants to buckle, and we're going to be unifying that with what we know from a standard coupon test in terms of the stress strain curve. So here is the whole thing unified. So this axis here would be the stress, and that would be this would be the Euler, so that would be that there. So that would be down there. So that would be your Euler, representing your pi squared EI over L squared. And then this portion here, so we've got the yield stress, which we've measured from the coupon, so that may be 300. Let's just say it's a number, and then here we might just like to draw a line there. Okay, so we're basically saying that anything that your structure or your material cannot take a load higher than the yield stress. So everything here above there is effectively redundant. So we can forget about that portion of the graph there, because we know that your material cannot take that stress. So obviously a short column is going to buckle at a much higher load than a long column, and we're saying that the short column is actually not going to buckle, but it's going to, the material itself cannot take that stress, so it's going to fail. So we can effectively forget about that. So let's read. As the critical stress cannot exceed the yield stress, there is a particular slenderness where they are equal. So we can define that point there. So let's draw this out here again. So they're equal. So you've got your Euler coming down there. And at that point, that's an interesting point, because sigma F, or your yield stress, is equal to the Euler stress. So that point there is interesting. So that intersection point there is interesting. So as critical stress cannot exceed the yield stress, there is a particular slenderness, lambda, where they are equal, and we can calculate that point where the material strength is equal to the Euler, or the buckling stress, and that one comes out as lambda naught, and that's equal to pi times the square root of E over sigma y. Okay, so that's where this thing called lambda naught comes from. So we just make these two equations equal, and then you can work out the lambda naught. So this value of slenderness separates two types of failure. Columns, anything here is called a short or stocky column. So anything here is called a short. Remember that's lambda, which is equal to L over R. So you work at the slenderness. If it's less than that value, then you call your column a short column, and if it's greater than that value, then you would call it a long column. And there's a transition between short and long. So this value is separated by two types of failure. The short column will fail through the material being crushed. Columns longer, or long columns, fail by Euler. So if a column is long, it will be failing by Euler. And this slenderness clearly depends on the material properties and some typical values. And then in reality, you've got a transition zone between the short column and the long column, which is where things become interesting. And sometimes we call those intermediate, or they call it here transition. So something clearly is short on this side here, something clearly is long, something here. And if you're not sure because it's around this area, we'll just loosely call it the transition. So in reality, the division between short and long columns is not that sharp. So your columns don't be your buckling curve, which we've drawn here, doesn't just go there and then suddenly at that point go downwards. That's just not reality of life. So in reality, maybe there's a smoother transition in nature between the short and the long, and then it would gradually go there. So maybe this is the true behavior. In nature, things don't just become sharp. So that you tend to get smooth lines, and of course columns are in nature. So you would expect a smooth line between the short and the long. So here at this end here, of course, it's going to fail through sigma y, and at this end here, of course, it's going to fail through buckling, and then we would expect a smooth transition, not a sharp transition, which I've just sketched there. So in reality, the division between short and long column types is not that sharp, and there is a transition zone. So taking this into account, the relationship at stress, failure and slenderness is shown in this figure by that solid line. And how do we get this solid line? Well, we can come up with some maths to help us curve fit, but that's all we're doing. We're just curve fitting. What we actually do is that we get experimental test data from universities and or column tests that have been conducted, and use that to curve fit. So anyway, we as engineers, we need some unified method to design columns, and tomorrow we'll conclude by explaining what some of these methods are.